Hello. In the evening session yesterday, I showed a long and drawn-out method for solving this problem from Hefferon. Find matrices P and Q to express H via PHQ as a block partial identity matrix. So that means I want to write find P and Q such that P times H times Q is a diagonal matrix with ones on the diagonal, and it may also have zeros on the diagonal. All right. So to solve this problem, we should consider H as a representation with respect to the standard basis. Right. In fact, that's what this matrix means. If I write a vector with respect to the standard basis, that's just our ordinary vectors, right? If I have 1, 2, 3 as a column vector, that's 1 times basis vector E1 plus 2 times basis vector E2 plus 3 times basis vector E3. And the result, whatever it is, will also have coefficients A, B, C. That's A times basis vector E1 plus B times basis vector E2 plus C times basis vector E3. So whenever you have a matrix, you can consider it as a representation with respect to the standard basis. Now, suppose we consider P and Q as change of basis matrices. We have this formula for the representation of the matrix H from basis B to basis D. So the way I read this, is that if I want to go from basis B to basis D, you read this from right to left. You go from basis B to basis E, then you take H, which is in the standard representation from E to E, and then you go from basis E to basis D. So remember, when you multiply column vectors, you multiply on the left, so you read from right to left. Now, so all I have to do is I need to find two bases, B and D, that gives me a diagonal representation of this matrix. If I find B and D such that the representation is diagonal, then this left-hand side will be diagonal. Then this will be my P, and this will be my Q. So I've changed this problem from an algebraic problem into a more geometric problem. How can I find two bases that makes the representation diagonal? All right, now, well, think about what happens. All right, so first of all, we have to notice if this matrix were singular, or non-singular, if this matrix were non-singular, then the answer would be very easy. I could simply choose P as the inverse of H. If H was invertible or non-singular, and P was the inverse of H, then I'd have P times H is equal to the identity, and that's no problem. But you find out under row reduction that this is not non-singular. In fact, it's singular. And you can notice that the first column plus 3 times the second column is 5 times the third column. Now, how would you notice that? Well, if you wanted to show these columns were linearly dependent, then you'd have to find some combination of these two to give you 0. Okay? So that naturally suggests you take the first column plus 3 times the second column, and that will give you a 0 here. And it turns out to give you a 5 up here and a 10 down here. Okay? So we had the first column plus 3 times the second column is 5 times the third column. So what does that mean? That means that this vector H times the vector 1, 3, 5. Now this is a column vector. I'm lazy. I don't want to write it as a column, so I write it as 1, 3 minus 5 transpose is equal to the 0 vector. Okay? Remember, this matrix equation here is a linear combination of the columns of H. H times this column vector means I take 1 times the first column of H plus 3 times the second column of H minus 5 times the third column of H. Okay? So I found a vector that maps to the 0 vector. Now what this shows me is that my representation is going to have a 0 column. You can see that this matrix has rank 2. Okay. So let me just write that in. It is clear the matrix H has rank 2. Okay. So that means, so the reduced form must also have rank 2. Must also have rank 2. Okay. So it must be this matrix. Let me insert my matrix. It must be this matrix, this one here. If it's rank 2 and it's one of these reduced diagonal matrices, this must be 0, this must be 0, this must be 0, this must be 1, this must be 0. And the last column must be all zeros. Okay. All right. Now look, I've essentially taken care of my last column, because the H times this column gives me a 0, 0, 0. So I'm going to include this in my basis B. Okay. All right. Now let's look at what H does to some other vectors. Well, obviously H to 1, 1, 1, 0, 0, that's going to pick out the first column of H. So that gets me 2, 3, 1. H of 0, 1, 0 gives me 1, minus 1, 3. And H of 1, 3, minus 5 gives me 0, 0, 0 t, transpose. Okay, so if I choose my basis D to have 2, 3, 1 as the first vector, that means it maps this vector to this vector. So the matrix transformation is basically the identity. If I change this have this as my basis vector B, this is my basis vector D, then the matrix transformation is going to be the identity, right? 5 times this basis vector is going to map to 5 times this basis vector. Okay. Similarly here, this if I choose my basis B vector to be 0, 1, 0, and my basis D vector to be 1, minus 1, 3, then this B2 vector will map to D2, so that's the identity transformation on that set of bases. Now here, 1, 5, minus 3 maps to 0, 0, 0. So this 1, 5, minus 3 maps to 0 times some vector. I can choose any vector here, as long as it's linearly independent from 2, 3, 1 and 1, minus 1, 3. Okay? So if I choose the 3 basis vectors, 1, 0, 0, 0, 1, 0, 1, 3, minus 5 for my B, and 2, 3, 1, 1, minus 1, 3, and any vector at all for my D, then my representation matrix of H is going to be 1, 0, 0, 0, 1, 0, 0, 0, 0. Okay? So really, I've almost solved the problem. Okay? By thinking about what the matrix does to bases, I can tell what the representation matrix is. All right. So now it's reduced to the algebra problem. I have to compute these other representation matrices, and we have a formula for that. Okay. So as I said, this third vector could be any vector as long as it's linearly independent from the other 2 vectors in D. Okay. I can simply choose 0, 1, 0, 0, 1. That's obviously linearly independent from these 2. There's no way that you could take a linear combination of these 2 and get 0, 0, 1. It just doesn't work. Okay. All right, so according to the formula, this rep BDH is equal to rep EDID times H times rep BEID. That's the same formula that I put up top, okay? But we want to rearrange this because we want to express H in terms of this representation, which has this nice form here. Okay. So here you just reverse the basis transformations. Here, this one I read rep from B to D goes rep from B to E, rep from E to E, E to D. Here I want to go, here H is from E to E, so I want to go from E to B, from B to D, and from D to E, back to E, back again. Okay. So I really just rearranged this equation and used the fact that rep DE is equal to the inverse of rep ED. Okay. Now, we've seen that the columns of this representation matrix are the basis vectors in D. So I did this example some time ago, and you can verify that. Okay. We also saw that if I want rep EB, if I want to go from E to B, that's the inverse matrix of the representation matrix from B to E. And the representation matrix from B to E is simply the matrix whose columns are the vectors in B. So here's my answer. H is equal to this vector here, which is the column vectors in basis D. Remember, I chose my third vector simply to be linearly independent from the other two. These two are the columns of my original matrix. Then I have this matrix here, and then I take the inverse of this matrix here. Now, the inverse of this matrix here is very easy to compute. Just use the technique of appending an identity matrix and row reduce. So if you take this matrix, append an identity matrix, and row reduce, you get this matrix here. This is kind of sloppy, but you can see this here, these three columns here are my inverse. So I get this result. So H is equal to this. And you can verify. Right? Now, how does this work? You can see how this works. Remember that if I do this, if I take this matrix product, okay, so this matrix product is going to have three columns. I'm just taking the first two first. Okay. The first column of the matrix product is this matrix times this column. What does this column do? Well, it picks out the first column of the matrix on the left. Okay. So the first column of this product is simply 2, 3, 1. Okay. So maybe I can show that instead of just waving in the air. So let's check it. If I want to take this product, so the first column is just equal to the matrix on the left times the first column on the right. Okay. And that's just equal, the first column on the right is simply going to pick out the first column of the matrix on the left. So it's just going to be equal to 2, 3, 1, and then that's going to be the transpose. Okay. I don't know why it didn't show the transpose. There's supposed to be a transpose there. Okay. So so the second column, I can just do the same thing with the second column. Just very same argument, right? Second column is the matrix on the left times the second column on the right. And that's going to be 1 minus 1, 3. Now this is great, because remember, what I want is this final result, 2, 3, 1, 1 minus 1, 3. I already got my first two columns all set. What about the third column? The third column is the third column here times, or the third column here times this matrix, and that just gives me 0. So the second column, the third column, is the matrix on the left times the third column on the right, and that's equal to 0, 0, 0. Okay, so I'm all set except for my third column. So what do I have? I actually now have, so the result is, sorry, now why is it doing that? Oh, here, let's try this. I think it's really totally screwed me up. Okay, here, so let's try this. This is weird. Okay, all right, so this is really weird. Okay, so anyway, I'll fix it. You just have to outsmart OneNote. It's very okay. So let me copy this. So the result is 2, 3, 1, 1 minus 1, 3, 0, 0, 0. Okay. All right, now I want to multiply this times the matrix on the right. Okay. I need to multiply this by here. Okay. So it's really kind of neat how the matrix on the left gets your first two columns all set. Then what does this one do? Well, so here, let's write down the product. I have this matrix here times this matrix here. Okay, what's that going to do? Well, just the same result. I'm not going to go through this in super detail, but remember that the first column of the product is the matrix on the left times the first column on the right. That's just going to be the first column here, 2, 3, 1. Second column for this matrix here times the second column, that's just going to be the second column of this matrix 1, minus 1, 3. Last column here is simply going to be the last is going to be this column up. The last column of the product is going to be the last column here times these two matrices. Now what is this going to do? It's going to take 1/5 times the first column plus 3/5 times the second column and then subtract 1/5 times the third column, which is 0. So in fact, it's just going to give me 2/5 plus 3/5. That's the linear combination that I found out before gives me the third column of this matrix. Okay. So what I'm going to get is simply first column is the same, second column is the same. This is just going to be, if I work this out, this is 2/5 and then plus 3/5. This next one here is going to be, what's going to be 3/5 and then minus 3/5. And the last one is going to be 1/5. See, what I'm doing is I'm multiplying these rows here by the last column here. All right. So last one is going to be 1/5, and then it's going to be plus 3/5. Okay. Okay. And that's simply, which is equal to the desired result. Okay. So let's do a recap here. We considered this problem of finding the partial identity form as a change of basis problem. I want to represent this H in terms of a different basis. I want to find a good basis, good pair of bases that represents this matrix in an easy way. All right. Now, if I simply chose the standard basis here for my B, then my basis D would be 2, 3, 1, 1 minus 1, 3, 1, 0, 2. But I have to make sure that all right, so hang on a second. Let me backtrack and say that again. If these columns were linearly independent, then I could simply choose these columns as my target basis, as my basis D. But these columns are not independent, so they don't form a basis. So what I do, actually, is I choose a basis that consists of the first two columns and some other vector. Right? And then I need to choose my basis B so that the matrix representation is the identity. So I can choose the first vector in basis B as 1, 0, 0, which will map to 2, 3, 1. That's going to be an identity transformation in terms of basis B and D. Choose my second vector, 0, 1, 0, which maps to 1, 1 minus 3, which is the identity transformation with respect to bases B and D. And then for the last one, I have to choose a vector that maps to 0. And that's what I did down here. And then I can choose for my third basis vector in D, I can choose anything because 0 is 0 times any vector. Right? So in this way, I found my two bases, D and B. And once I found my two bases, B and D, I just used the matrix representation formula to convert this H in standard basis to H in terms of bases B and D. All right. So this is worth thinking about. I think it's not obvious, but it's worth thinking about how this PHQ really is a change of basis formula, as long as P and Q are invertible. If P and Q are not invertible, then they're not change of basis matrices. Okay, that's it. Hope you enjoyed it.